Deduction and Induction. Logicians make an important distinction between deductive and inductive patterns of reasoning. An example of a piece of deductive reasoning, or a deductive inference, is the following. All Frenchmen like red wine. Pierre is a Frenchman. Therefore, Pierre likes red wine. The first two statements are called the premises of the inference, while the third statement is called the conclusion. This is a deductive inference because it has the following property. If the premises are true, then the conclusion must be true too. In other words, if it's true that all Frenchmen like red wine, and if it's true that Pierre is a Frenchman, it follows that Pierre does indeed like red wine. This is sometimes expressed by saying that the premises of the inference entail the conclusion. Of course, the premises of this inference are almost certainly not true. There are bound to be Frenchmen who do not like red wine, but that is not the point. What makes the inference deductive is the existence of an appropriate relation between premises and conclusion, namely that if the premises are true, the conclusion must be true too. Whether the premises are actually true is a different matter, which doesn't affect the status of the inference as deductive. Not all inferences are deductive. Consider the following example. The first 5 eggs in the box were rotten. All the eggs have the same best before date stamped on them. Therefore, the 6th egg will be rotten too. This looks like a perfectly sensible piece of reasoning, but nonetheless it is not deductive, for the premises do not entail the conclusion. Even if the first 5 eggs were indeed rotten, and even if all the eggs do have the same best before date stamped on them, this does not guarantee that the 6th egg will be rotten too. It is quite conceivable that the 6th egg will be perfectly good. In other words, it is logically possible for the premises of this inference to be true, and yet the conclusion false. So the inference is not deductive. Instead, it is known as an inductive inference. In inductive inference, or inductive reasoning, we move from premises about objects we have examined to conclusions about objects we haven't examined. In this example, eggs. Deductive reasoning is a much safer activity than inductive reasoning. When we reason deductively, we can be certain that if we start with true premises, we will end up with a true conclusion. But the same does not hold for inductive reasoning. On the contrary, inductive reasoning is quite capable of taking us from true premises to a false conclusion. Despite this defect, we seem to rely on inductive reasoning throughout our lives, often without even thinking about it. For example, when you turn on your computer in the morning, you are confident it will not explode in your face. Why? Because you turn on your computer every morning, and it has never exploded in your face up to now. But the inference from, up until now my computer has not exploded when I turned it on, to, my computer will not explode when I turn it on this time, is inductive, not deductive. The premise of this inference does not entail the conclusion. It is logically possible that your computer will explode this time, even though it has never done so previously. Other examples of inductive reasoning in everyday life can readily be found. When you turn the steering wheel of your car anti-clockwise, you assume the car will go to the left, not the right. Whenever you drive in traffic, you effectively stake your life on this assumption. But what makes you so sure that it's true? If someone asked you to justify your conviction, what would you say? Unless you are a mechanic, you would probably reply, every time I've turned the steering wheel anti-clockwise in the past, the car has gone to the left. Therefore, the same will happen when I turn the steering wheel anti-clockwise this time. Again, this is an inductive inference, not a deductive one. Reasoning inductively seems to be an indispensable part of everyday life. Do scientists use inductive reasoning too? The answer seems to be yes. Consider the genetic disease known as Down syndrome, DS for short. Geneticists tell us that DS sufferers have an additional chromosome. They have 47 instead of the normal 46. How do they know this? The answer, of course, is that they examined a large number of DS sufferers and found that each had an additional chromosome. They then reasoned inductively to the conclusion that all DS sufferers, including ones they hadn't examined, have an additional chromosome. It is easy to see that this inference is inductive. The fact that the DS sufferers in the sample studied had 47 chromosomes doesn't prove that all DS sufferers do. It is possible, though unlikely, that the sample was an unrepresentative one. This example is by no means an isolated one. In effect, scientists use inductive reasoning whenever they move from limited data to a more general conclusion, which they do all the time. Consider, for example, Newton's principle of universal gravitation, encountered in the last chapter, which says that every body in the universe exerts a gravitational attraction on every other body. Now, obviously, Newton did not arrive at this principle by examining every single body in the whole universe. He couldn't possibly have. Rather, he saw that the principle held true for the planets and the sun, and for objects of various sorts moving near the Earth's surface. From this data, he inferred that the principle held true for all bodies. Again, this inference was obviously an inductive one. The fact that Newton's principle holds true for some bodies doesn't guarantee that it holds true for all bodies. The central role of induction in science is sometimes obscured by the way we talk. For example, you might read a newspaper report that says that scientists have found experimental proof that genetically modified maize is safe for humans. What this means is that the scientists have tested the maize on a large number of humans, and none of them have come to any harm. But, strictly speaking, this doesn't prove that the maize is safe, in the sense in which mathematicians can prove Pythagoras' theorem, say. For the inference from the maize didn't harm any of the people on whom it was tested to the maize will not harm anyone is inductive, not deductive. The newspaper report should really have said that scientists have found extremely good evidence that the maize is safe for humans. The word proof should strictly only be used when we are dealing with deductive inferences. In this strict sense of the word, scientific hypotheses can rarely, if ever, be proved true by the data. Most philosophers think it's obvious that science relies heavily on inductive reasoning, indeed so obvious that it hardly needs arguing for. But, remarkably, this was denied by the philosopher Karl Popper, who we met in the last chapter. Popper claimed that scientists only need to use deductive inferences. This would be nice if it were true, for deductive inferences are much safer than inductive ones, as we have seen. Popper's basic argument was this: although it is not possible to prove that a scientific theory is true from a limited data sample, it is possible to prove that a theory is false. Suppose a scientist is considering the theory that all pieces of metal conduct electricity. Even if every piece of metal she examines does conduct electricity, this doesn't prove that the theory is true, for reasons that we've seen. But if she finds even one piece of metal that does not conduct electricity, this does prove that the theory is false. For the inference from, this piece of metal does not conduct electricity, to, it is false that all pieces of metal conduct electricity, is a deductive inference. The premise entails the conclusion. So if a scientist is only interested in demonstrating that a given theory is false, she may be able to accomplish her goal without the use of inductive inferences. The weakness of Popper's argument is obvious, for scientists are not only interested in showing that certain theories are false. When a scientist collects experimental data, her aim might be to show that a particular theory, her arch-rival's theory perhaps, is false. But much more likely, she is trying to convince people that her own theory is true, and in order to do that, she will have to resort to inductive reasoning of some sort. So Popper's attempt to show that science can get by without induction does not succeed. Hume's problem. Although inductive reasoning is not logically watertight, it nonetheless seems like a perfectly sensible way of forming beliefs about the world. The fact that the sun has risen every day up until now may not prove that it will rise tomorrow, but surely it gives us very good reason to think it will. If you came across someone who professed to be entirely agnostic about whether the sun will rise tomorrow or not, you would regard them as very strange indeed, if not irrational. But what justifies this faith we place in induction? How should we go about persuading someone who refuses to reason inductively that they are wrong? The 18th century Scottish philosopher David Hume, 1711 to 1776, gave a simple but radical answer to this question. He argued that the use of induction cannot be rationally justified at all. Hume admitted that we use induction all the time, in everyday life and in science, but he insisted this was just a matter of brute animal habit. If challenged to provide a good reason for using induction, we can give no satisfactory answer, he thought. How did Hume arrive at this startling conclusion? He began by noting that whenever we make inductive inferences, we seem to presuppose what he called the uniformity of nature, UN. To see what Hume means by this, recall some of the inductive inferences from the last section. We had the inference from, my computer hasn't exploded up to now, to, my computer won't explode today. From, all examined DS sufferers have an extra chromosome, to, all DS sufferers have an extra chromosome. From, all bodies observed so far obey Newton's law of gravity, to, all bodies obey Newton's law of gravity, and so on. In each of these cases, our reasoning seems to depend on the assumption that objects we haven't examined will be similar, in the relevant respects, to objects of the same sort that we have examined. That assumption is what Hume means by the uniformity of nature. But how do we know that the UN assumption is actually true? Hume asks. Can we perhaps prove its truth somehow, in the strict sense of proof? No, says Hume, we cannot. For it is easy to imagine a universe where nature is not uniform, but changes its course randomly from day to day. In such a universe, computers might sometimes explode for no reason, water might sometimes intoxicate us without warning, billiard balls might sometimes stop dead on colliding, and so on. Since such a non-uniform universe is conceivable, it follows that we cannot strictly prove the truth of UN. For if we could prove that UN is true, then the non-uniform universe would be a logical impossibility. Granted that we cannot prove UN, we might nonetheless hope to find good empirical evidence for its truth. After all, since UN has always held true up to now, surely that gives us good reason for thinking it is true. But this argument begs the question, says Hume, for it is itself an inductive argument, and so itself depends on the UN assumption. An argument that assumes UN from the outset clearly cannot be used to show that UN is true. To put the point another way,